Hello, students. We're going to be solving some equilibrium problems today. You're going to need to use all the concepts that you've studied in sections 13.1 through 13.5. And I think as we work some problems, maybe some things will make a little bit more sense as in regards to those concepts. What I'd like you to do or suggest that you do is to go to the Zoom discussion for next week, and in there are these Zoom equilibrium questions. So if you want to follow along on paper, that's fine. But these are all from that handout. Okay, let's go ahead and get started. Here we have a reaction that's giving us a Kp, 6.5 times 10 to the negative 4 at 308 Kelvin. I'm going to stop here for 1 second and tell you that the temperature is given. This is always given because K is temperature dependent. You may not use that temperature in the problem though, but they're going to be thorough and give that to you. Okay, so at equilibrium, there's a partial pressure of NO as 0.35, partial pressure of chlorine at 0.10, and then we want to know what's the equilibrium partial pressure of the product NOCl. So what we want to picture is that within our container, we began this reaction with NO and Cl2, and they collided and reacted to make product. So you had a forward reaction, and then you also had a reverse reaction kick in. So what would happen here is that at equilibrium, you have a mixture of all three of these. So this is first number one concept, is that these reactions are not going to completion. We're in the reversible moderate range equilibrium section. And so because of this, you have to adjust your thinking, because in Chem 200, we looked at reactions that like to go one way, which was forward. Whereas in this case, this gas phase reaction, the reactants go make product, the product comes back easily to make reactants. Once those rates hit, we end up with a mixture of all three. Okay, so that is a really important thing. Oops, I didn't mean to get that big blobby. All right, so that's a really important thing, is that we have a mixture of all three of these. Now, one thing you've learned from previous chem is that gases exert a pressure on the walls of their container. So the partial pressure of NO at equilibrium is 0.35. The pressure of the chlorine at equilibrium is 0.10 atmospheres. So the question is, what is NOCl's pressure? And we are provided insight into that because the Kp is the ratio of pressures. Now let's go to our balanced equation. That means the pressure of NOCl squared, because of the 2, divided by the pressure of NO squared, because of this 2, divided by the pressure of chlorine. So if we're looking at that, we are really asking, what's the pressure of NOCl at equilibrium? And so we would just plug in. Okay, so we're going to solve for pressure of NOCl, and I don't have you to double check me, so I have my answer worked out, but I'm just going to double check it one more time. Okay. I got 2.8 times 10 to the negative 3. Okay, now when we're doing this, keep in mind that we can always double check our answer because we can square that term, right? We can square 2.8 times 10 to the negative 3. And then we can divide by 0.35 squared and then divide by 0.10. And we should end up with our original KP, which I do. Okay, a couple comments. Number one, most important thing is we worked the problem with pressures. So do not be afraid of pressures. You can work equilibrium problems in pressures. We do not have to change it to concentration. We do not have to convert KP to KC. None of that is necessary here. Okay, and that is a really important thing because sometimes students on the exam, when faced with this question, they start doing work, not only that's not needed, but then they completely don't do the part that is. So it is not necessary to convert this KP to KC. We just will plug in everything in terms of pressure. Okay, that's a very important thing. Secondly, is that in reversible reactions, we end up with a mixture of all species at equilibrium. So we have to let go of those reactions that we did in Chem 200, which went one way. This one goes both ways. It's reversible. Okay, lastly, it didn't come up here, but there are some questions that talk about asking for like total pressure. Keep in mind that the total pressure in this system is a sum of all the individual partial pressures. That would be Dalton's law from Chem 200 when you did gas laws, Dalton's law of partial pressures. So, there's some questions that might address that piece. I am saying this because I can't do every single style of question out there. So we have to kind of think things through. So just relating this to previous stuff is that if the question asked for the total pressure, you would just sum the individual pressures. Okay. One other thing before I click on this guy is this is our easiest type of question. We are already at equilibrium. So when they're already at equilibrium and they give you the numbers, it tends to be straightforward. You just plug into the K expression. Okay, next one. 0.0050 moles of hydrogen and 0.010 moles of I2 were placed in a 5-liter container and allowed to come to equilibrium at 448 degrees Celsius. At equilibrium, 0.00187 molar of HI was found. What is the Kc for this reaction at this temperature? Okay, again, temperature, this 448 is just there because they're being thorough. Don't need to worry about that. Let's think this through. I start off with a certain amount of hydrogen and iodine in a 5-liter container. So I'm being asked for Kc, which is concentration. So the first thing I should probably do is convert those guys to molarities. So I'll do the first one written out, but then the second one we'll just do quick. 0.0050 moles in 5 liters. Okay, so that's going to mean that our concentration, we'll need to find it, right? So if we're going to say, okay, I'm going to take 0.0050 divided by 5 is 0.0010 molar, correct? So our concentration is 0.0010 molar in H2. Okay, if I do the same thing for the I2, then we're going to get 0.0020 molar I2. Now at this point, as we keep moving forward, there's going to be things now where maybe we don't need to show this part, right? This should be easy now. Molarity, moles per liter. Okay? All right. Now that's our initial flasks. That's our initial conditions. And after it sits around and reaches equilibrium, we're going to end up with a mixture of H2, I2, and HI. That's because the product forms and then comes back, and then the rates equalize. So at equilibrium, we have a mixture of all three. This is different than having it from last semester where they react and then you have a limiting reagent and you end up with 0 of the limiting reagent, you have an excess, and then you have your product. See here, the reaction goes forward, it goes back. When the rates equalize, we have a little bit of everybody in there. Okay, so let's go ahead and write our KC expression, concentration of HI squared over H2 and I2. The thing is, implied in this, like from the last question, is that these are equilibrium amounts. Equilibrium amounts are not initial. So we have some extra work then to do here. So I'm going to write my equation, H2 gas plus I2 makes HI. And now we need to think. I'm going to kind of think things through to help us out. We use what are called ice tables. And the ice tables look like this. I'm going to show my initial conditions, and I'm going to write down 0.0010 molar for H2 and 0.0020 molar for I2. Okay, now I need to think about how the question was worded. Initially, I had 0 of the HI, correct? We saw the initial amounts of H2 and I2, and they were placed in a 5-liter container. There was no HI placed in there. Okay, we know that at equilibrium, I'm going to show that as E. What's given is we know how much HI was in there. Okay, so on our KC expression, I do know HI. I have that number. That is given. But I do not know how much hydrogen and iodine are there yet. Okay, so here comes the really, really important conceptual part. The reaction could only go one way initially. Initially, to reach equilibrium, this had to go towards product. Why? Because I didn't have any product starting there. It can't go backwards yet. So this for sure shifts to the right to reach equilibrium. It doesn't go to completion, meaning that there's a change. Because remember, I end up with a little bit of all of them at equilibrium. So it shifts, but not 100% completion. So I don't know the amount, and I'm going to call that X. From the stoichiometry, we also know the iodine shifts to that amount as well. So X is the change, how much reacted. Okay, it's some amount, some portion of those two. Now on this side, HI, from the mole ratios, we know that the mole ratio is 1 to 1 to 2, so we are adding 2X. That's because twice as many moles form. Okay, so I'm looking at this. Again, it has to shift right to reach equilibrium because we just have reactants. And then now I have a starting point where I started HI at 0. 2x reacted to make 0.00187. So 2x, I'll write it over here, 2x equals 0.00187. So I can figure out the change, right? That's the change would be 0.00187 divided by 2. That's 9.35 times 10 to the negative 4 molar. Okay, that's how much it shifted. So 0.001 minus this number minus this number gives us the amount of hydrogen, 6.5 times 10 to the negative 5. That's how much is left at equilibrium in the flask. For iodine, it's going to be 0.0020 minus that x. Okay, so if we take 0.002 minus the x, I got 1 point, let's see, hold up. Basically 1.07 times 10 to the negative 3. Okay, so let's recap. We started with hydrogen and iodine. Has to shift right because there wasn't any product. As the product accumulates, some shifts back, and then equilibrium is reached. We know the equilibrium amount of HI. Notice it went from 0 to 0.00187, so we know it did shift right. It's more of it, right? We also know that these reactions are not like last semester. You don't end up with like 0 hydrogen or 0 iodine. We say some of it reacts, minus X, minus X. There's an amount that it shifted or reacted to reach equilibrium. On the other side, it's 2X. That's from the mole ratio. We found our change, our X, by taking 2X equal to the equilibrium amount, and then now we go and plug in. Ultimately, what we're going to do is we'll plug into Kc expression. Okay, and probably the sig figs are a little funny on that 1.07, but that's okay. We can use more digits. And then we'll plug all this in, squaring the top. And I got 50.3 for the Kc. And our sig figs are debatable. Some of these have a really small number of like when you do the subtraction. So this would be at the most 50.3. You can go through and analyze the sig figs more, but it's either the precision's probably not that great, probably to 50. Okay, just because our concentrations are 0.0010 has a lot of decimal places, but when you do that subtraction, you're probably only going to have 2 sig figs for when you go in the division. Okay. All right. So that's a really, really typical question. And we do have to think things through, okay, on what's given and where we want to go. Okay, let's try another one. In a reaction, 2 molar CO is mixed with 1 molar water. If Kc is 1.56, what are the equilibrium concentrations of all species? Okay, so again, we have initial amounts, right? Those are given as initials. So we're going to set up our ice tables. Okay, those are our initial values. Set our change. Okay, so initially we don't have any of the products. And then we want to think, once again, it's going to shift to the right because I don't have any products. It can only go that direction right now. Okay, so for sure, we're going to shift to the right. So I'm going to say minus x, plus x, plus x. They're all 1 to 1. Okay, now I go look up at the question, and I'm not given any information regarding equilibrium amounts. So this is 2.00 minus x, 1.00 minus x, x, and x. So let's see what we do have. We know the Kc is 1.56, and now we want to solve for the equilibrium amount. So I need this x. So let's set up our Kc expression and see if that helps us. So we're going to say Kc so x times x, so that's x squared there at the top. That equals 1.56. So now I have my x squared over 2 minus x times 1 minus x equals 1.56. And we're probably now thinking, oh no, this doesn't look good, right? Because I have to solve for x now. Okay, so let's think about how we would go about solving for x. First thing we'd probably think is we're going to clean this bottom part up. So I'm going to switch this bottom part FOIL, right? So I'm going to have 2 times 1, 2, minus 2x, minus 1x, plus x squared. And then that's going to combine at the bottom there, 2 minus 3x, plus x squared. Okay, we're still feeling a little nervous. Let's go to the next slide. I have a little more room. So I'm going to say, rewrite that, x squared over x squared minus 3x plus 2 equals 1.56. So now I'm going to bring that bottom part to this other side. And then we're going to distribute. And now we're starting to get perhaps a little bit of a sinking or excited feeling about where we're headed with this. So I'm just distributing. So at this point, you should start to think, how are we going to solve this equation? And maybe you know the answer, but let's clean this up. At this point, we need an equation that will deal with these squared terms in this format. And the way we solve this is to set this equal to 0. to finish that off, I'm going to have to subtract 1x from both sides. So I'm going to get 0 equals 0.56x squared minus 4.68x plus 3.12. And at this point, we need quadratic equation. Now, this is an exciting day for your math teacher, because your math teacher always told you that you were going to need quadratic for some other class. And here is that day. This is when we need quadratic in chemistry. So that's pretty exciting for your math teacher. And so we'd go ahead and plug in. A is 0.56, B is negative 4.68, and C is 3.12. So go ahead and solve for that. And when you're done, you're going to end up with two roots. One of them is 7.63, and the other one is 0.73. So there's only going to be one that makes sense for the chemistry. So let's go ahead and take a look at that. And then let me make sure that I wrote everything correctly. Yeah. Okay, so let's come back here. My roots were 7.63 and 0.73. Only one of them makes sense based on the chemistry. So which one is it that makes sense? If you said that the 0.73 was the one that made sense, you are correct. Oops, I didn't mean to use that color. Yikes. I don't know why it's battling me now. Okay, now why does that X make sense? That B 0.73 is that we only have 2 molar and 1 molar to start. You can't react 7.6 molar when you didn't have that to begin with. So this is always going to happen, is that there's one X that makes sense for the chem. The top one does not. Too much, right? You can't react more than you have. Okay, so now what does this mean is I know my X, it's 0.73. Sorry, it looked like I was crossing it out. I think it's just that. Let me erase that purple there. Boy, this kind of, there we go, we're back. Okay, so that's our X. And now I can plug in, right? If that's my X, I'm going to subtract 0.73, 0.73. Here, this is plus 0.73, 0.73. So when I do that, I can see the following, that we end up knowing all of our equilibrium amounts. Okay, I'm going to use a different color for that. I'll go with the green. So this would be 0 plus 0.73 is 0.73. 0 plus 0.73 is 0.73. This is 1 minus 0.73, which is 0.27. And then this one is 2 minus 0.73, which is 1.27. Okay, and then I can plug in. So I can now say, I know all these now, right? And I can double check myself if I wanted to. Let me go back. Boy, that one little key is really giving me a hard time. I think it must be exactly where I need to be, but normally it's not that sensitive. Okay, so we can double check ourselves if we wanted to. We could double check, right? 0.73 times 0.73 divided by 1.27 and 0.27. If we plug those in, so go ahead and try that to double check if we did it right. I get 1.55, so that is very close to the 1.56. That's just a rounding thing. So we're good, right? That is what we're double check ourselves. We did the problem correctly. So these are the equilibrium amounts. Okay, so recapping, we have our initial amounts. It shifts to the right because there are no products, so it has to go right. And then we set up our equilibrium chart, our ice table. We set up our KC expression, and using quadratic equation, we solved for x. Come back and plug in for x and get our equilibrium amount. Okay, this last example, ammonium hydrogen sulfide decomposes according to the following reaction for which Kp is 0.11. If 55 grams of the solid is placed in there, what is the partial pressure of ammonia at equilibrium? What's missing from here is the equation. That would be given. I just didn't type it in there. Okay, I want to do this one with you because I want to prove to you how important it is to know the concepts. We have a solid. We have a solid. It's decomposing into the gas. The gas is coming back into the solid and they reach equilibrium. So you have the two gases in there. Recall that this is what's called heterogeneous equilibrium, meaning you have the solid with the gas. But our K expression, our Kp, or K for this, is the pressure of hydrogen sulfide times the pressure of ammonia. So the solid doesn't appear in the equilibrium expression. So if we want to think of our ice chart, probably shouldn't have written that there. I think I'm going to erase it and move it over. If we think of our ice chart, go ahead and write the ice expression for this. We have 55 grams in 5 liters. That you can go to the molarity. Some of it's reacting. And then you have your equilibrium amount. But what I want to show you is that the solid there is not part of our calculations because it doesn't appear in the Kp expression. Okay, so the solid amount is extra info. Now, sometimes that makes students mad that there's extra stuff you don't need. Like you don't need the temp, you don't need the grams. Okay, that's why the concept is so important. I've seen this question worded a little bit differently in other texts where they'll say solid ammonium hydrogen sulfides added. So they don't give you like the 55 grams, but they do tell you because you have to have that. That's the reactant, right? So you have to have some there. It's just that the Kp expression is going to be in terms of just these two pressures. So this is not needed for this question. And then if you think about it, wow, this can be really easy. 0.111 equals x times x, which is x squared, and x will equal the square root of that. So I think that's 0.67. Oh, no, sorry, 0.33. Okay, also we know that we have to shift this, initially has to shift to the right because we don't have any present initially. It's only at equilibrium that these guys are present, or, as it's approaching equilibrium. Okay, so again, this problem also shows us that we can work equilibrium problems in pressure. We don't need to convert to concentration. I don't need to go to Kc. That's not needed here. The other thing that's important here is solids and pure liquids are not included in the K expression. And so the Kp here is based on pressure. That's why it's Kp. And it's just the pressure of hydrogen sulfide and ammonia. Okay, so we set up our ice table, not needing the solid information. And then we know that the equilibrium amounts of the two gases are X, and we set those equal to Kp. Okay, so this is a good starting point. Please start your homework on this section. And then on the Zoom lecture discussion for this on Monday, we will talk a lot more about this. So this is a really critical part for your exam 1.